Okay. So basically for inorganic chem, right, there's 4 chapters lah. Okay. So the 4 chapters being period 3, group 2, group 17, and then TM. Okay, so these 4. Okay, so for period 3, okay, period 3 is a bit more difficult. Why? Because you have a lot of reactions and a lot of things to remember. Okay. So for period 3, in this case, you have stuff like for period 3, you have things like first they will ask you for your normal metals lah. So they'll ask you for the trends down the period first. Trend across your period. Okay. They may also ask you on their chlorides as well as their oxides. Okay, and with their respective like melting point, boiling point, your reactivity with water, reaction with water, so on and so forth lah. Okay, so this is the one which is the most tedious because why period 3 is a lot of things to remember. Okay, and there's a lot of exceptions as well. Okay, then we have group 2. Group 2 mainly is they will ask you for trends down the group. Okay, so things like your reactivity, your ionic radius, your IE and stuff like that. Okay, that one's quite common. Okay, they may also ask you your stability of your salts. So stability of your salts. Okay, so the salts can be your hydroxide, can be your carbonate, can be your nitrate, can be your sulfate. Okay, so these are the other ones, also stability of salt. So this stability of salt. So these are the ones for group 2. Okay, for group 17, okay, same thing. Your trends down the group. Okay, so things like your melting point, boiling point, trends down your group. Okay, or they will ask you your reactivity and your stability. Okay, the stability here is of your HX. Okay, and they ask you for reactivity. Okay, reactivity in terms of being an oxidizing agent. Okay, because group 17, the halogens, right, they themselves want to be reduced. So as they are reduced, right, they oxidize another compound. Okay, so that's why they are oxidizing agents. Okay, then last but not least, we have TM. Okay, TM, you have your physical properties and your chemical properties. Okay, so physical properties like your melting point, boiling point, density, okay, and your LE. Okay, for IE, sorry. Then your chemical properties will be your variable oxidation states, able to show your different colors, okay, your ligand exchange. So these are the few different ones for TM. Okay, so in this case, actually, if you look at the bulk across all of these inorganic topics, right, mostly will come out from period 3, if not TM. Okay, however, I would say that period 3, they tend not to test anymore. Why? Because there's a lot of memorization. And sad to say, SEAB wants to move away from memorization. They want to apply more. Okay, so that's good. So period 3 will come out. Okay, usually group 2, group 17 will come out, and then TM will come out. These are the more common ones. Yeah, but there's less memorizing involved. So they tend to prefer less group 2 and group 17 because yes, it's still memorizing. However, there's less memory work to it. Yeah, but take note, they may also ask you a case where they ask you for the diagonal relationship. Because there's one question that I've seen, right? They test on group 1. They don't test on group 2 and group 17. But they expect you to know from your diagonal nature. Okay? So things like that you need to take note lah. Okay, so yes, it may be still inorganic chem. However, they ask you to apply the inorganic chem concepts, which will be a bit more difficult. Okay, so then it depends lah. But TM usually is by itself. Because TM, right, in this case is intro to TM lah. Okay, so your TM is not very, very difficult because it's just knowing how the physical properties are. That one is memory work lah. Okay, then for your chemical properties, that one you need to know how to understand and how to write lah. Okay, because the context itself can always be different. Okay, but the explanations are always the same. Okay, so these are the things that they ask you to do. Okay, so that's for inorganic chem. Okay, we also have electrochem. Electrochem, 2 sections. One is your galvanic cell, and the other one is your electrolytic cell. Okay, so now actually for electrolytic cell, right, we don't deal with whether it works or not, and what happens in the specific cell lah. Okay, because in this point, right, when we talk about electrolysis, right, we are doing more calculation based. Okay, so yes, the concept of selective discharge and stuff like that, right, is still present. However, it's less likely to be tested lah. Okay, they would like to prefer to test you on your quantitative. So they prefer to ask you to calculate. Okay, So that is that. Okay, for galvanic cell now, okay, you do a lot more on galvanic cell lah. It's the one that creates the voltage. Okay, the one that you need to produce to check whether it's feasible or not lah, stuff like that. Okay, I need to explain what will happen when it changes. That is what will happen for EChem. Okay, so I would say that these two topics, these two subtopics, right, your inorganic chem and EChem, right, come out very, very rarely. Okay, usually maybe you will see maybe 1 or 2 questions in paper 2, maybe 1 or 2 questions in paper 3 lah. That's about it. Because majority of the questions tested, right, will be on physical and your organic chem. Okay, so if you do the rough gauge, right, it will probably be 30-30 and maybe 10-10 or 15-5. Okay, what I mean by that? Okay, so 30% physical chem, 30% organic chem. Okay, then maybe 15 to 10% of your inorganic. Okay, and then probably about 10 to 5% of your EChem. This is usually the rough gauge of papers lah. Okay, because they tend to love to prefer to test organic and physical. Why? Because those are more application based. Okay, so this is just a rough gauge lah. Okay, but take note, your physical chem questions and your organic chem questions can be merged together. Okay, so they can give you an organic compound, so let's say your amino acids, and then test you on buffer. So it's common lah, they can test like that. Okay, so take note of the idea here lah. But inorganic chem and EChem, right, usually are by themselves. They tend to not mix them together with other topics. Okay, so it's quite difficult. Okay, so take note of that. Okay, so we look through the first question, question 1. This question is on period 3 elements and their respective chlorides. Okay, so this is a memorizing question lah. Okay, so in this case, they ask you to explain the trend. Okay, explain the trend in your melting point. Okay, so you can memorize one. Why? Because it's just a trend. So explain. So they're explaining that from sodium to silicon it goes up. Okay, and then after phosphorus to argon, right, it's going down. Okay, so you need to explain accordingly. Okay, so for Na, Mg, and Al, they are all metallic. Okay, so what does metallic mean? Okay, is strong electrostatic forces of attraction. Okay, electrostatic forces of attraction. Okay, but take note, this is between your cation and your C of delocalized electrons. Okay, so take note, this is the bonding. Okay, and why from sodium to magnesium to aluminium, why it increase, right? It's because the increased number of your valence electrons that are in your delocalized C of delocalized electrons. Okay, so you need to explain there's 2 parts to this 1 mark lah. Okay, the 1 mark is the first half is the talking about the forces of attraction between your sodium, magnesium, and aluminium. Okay, your metallic bonding. Okay, then the second part here, so is number 1. Okay, number 2 here, you need to say that your sodium, okay, is smaller than your Mg, smaller than your Al. Why? Okay, due to increasing number of electrons, increased number of valence electrons in your C of delocalized electrons. Okay, or you can state that your the bond strength, right? Okay, your bond strength is directly proportional to Q over R. So you use that because in this case, your ionic radius of Na, Mg, and Al should be roughly the same. Okay, so the fact that Q increases, this means that your bond strength should increase. Okay, so you can use either or. So for number 2, right, either use the first one or the second one. Both are fine. Okay, both are accepted. Okay. That one is not important here. It's just because your proton number equals your electron number. Okay, so in this case, it's the fact that the charge is higher, like yes, but because your proton number is higher, right, your charge is higher, so you have more electrons outside also, so it's stronger strength. That's it. Because the fact that your number of protons are increased, right, that was already accounted for. Because your charge increases. Sorry?
Why do you say the size of the cation?
No, this is the size of cation, right? The ionic radius, right? You're talking about second part here. This is only because your ionic radius is about the same. You don't need to care about the radius to be very fair. Because what your charge, the charge difference, right, is much greater than your ionic radius difference.
So why is it cation
Because in this case you're forming your ions, it's not your ionic radius, it's not your atomic radius. Which part are you talking about? Your bond strength here, right? The bond strength directly proportional to Q over R, right? Okay, it's your ionic radius, not your atomic radius. Because in this case, right, in the metallic structure, right, in your giant metallic structure, right, it is your cations and your C of D localized electrons. So it's your ionic radius, not your atomic radius. Okay, so take note of the difference.
Then when do you use the atomic radius?
Atomic radius usually you won't use unless you're talking about covalent. Because remember, ionic and metallic, right, they're using your ions. That's why it's ionic radius. However, for covalent compounds, right, they don't exist as ions, so they exist as atoms or molecules, but the molecules are made of atoms. So there's a difference. Okay? So next we look at silicon. Okay, so silicon is large covalent. Okay, so given as large covalent, okay, so this is your strong covalent bonds. Your strong covalent bonds. Okay, so in this case, since there are strong covalent bonds in a giant covalent structure, therefore a large amount of energy is required to melt your silicon. That's it. Okay, so this one mark is quite easy to get because it's just your strong covalent bonds. Okay. Then now we move on to, okay, so in this case you want to include argon, can, okay, but it's just phosphorus to this period here, so phosphorus to argon, okay, if you want to state that. Okay. So why do they have low melting points? Okay, this is because they have ID forces. Okay, remember whenever you're writing in the exam, right, write down instantaneous dipole, induced dipole, and then you bracket ID. So you can use the word, you can use the term ID afterwards. Okay, so this is due to ID. Okay, in the simple covalent structure. Okay, so take note here. Okay, your electron cloud size. Okay, sulfur 8 is greater than your phosphorus 4. Greater than your chlorine 2, greater than your argon. So this is your MR lah. Okay, so this is your MR. Okay, so since your MR, your silicon is the greatest, right? Followed by your phosphorus, followed by chlorine, followed by argon. Okay, your electron cloud size. Okay, it's also the same. So it's silicon 8. Okay, phosphorus 4, chlorine 2, argon. Okay, so therefore your polarizability also polarizability of E cloud lah. Okay, it's also the same. S8 greater than P4 greater than Cl2 greater than AR. Okay, so therefore your strength of your ID, okay, should be the greatest in your silicon, your sulfur 8, then your phosphorus 4, then your chlorine 2, then your argon. Okay, this one you don't need to memorize. Why? Because if they give you the graph here, right, you can just copy accordingly. Okay, but if you want to take note, yes, phosphorus is 4, sulfur is 8. Okay, chlorine is 2, and then argon is just by itself. If you really want to remember lah. Okay, so this one is talking about the extent of your ID forces.
Why simple molecular is not good?
Because in this case, simple molecular, right, you need to understand that simple molecular is just the two by itself. It's bonded covalently. However, they do not have enough space, right, to bond even more. So in this case, for giant covalent, right, the structure here, it looks like this. The giant structure looks like this. So it's like one molecule, right, bonded to many others. Okay, so something like this. Okay, so this is for your giant covalent, large covalent. Okay, however, for your simple covalent, right, it usually exists as this. So it's like double, right, and then there's intermolecular forces, double. The intermolecular forces, double. So they're not the same. Because they do not form any other covalent bonds. They just form covalent bonds with the other molecule, right, and then that's it. So the rest of the total lines are all your weak intermolecular forces. So yes, they are still in lattice. However, in this case, they are not bond. The forces between the molecules, right, are not strong. They are weak. So it's the difference. So you need to look at the different structure. Because why? They are not able to form any other covalent bonds. Because for silicon, right, in this case, why is it like that? Right? It's because the electron cloud, right, is too big. Okay, and it cannot form any double bond or any triple bond because your p orbital is very small compared to the radius lah. So the overlap is not effective because it's too far away. Because it's your 3s and 3p, right? Your 3p is too far away to merge with another 3p. So that's why we don't form double bonds. Okay? So in this case, why it only forms single bonds. So that's why you can continuously join the single bond all the way down. Okay, but for carbon it's different. Why? Because carbon can exhibit hybridization. Silicon cannot. Okay? So that's why it only forms your single bonds. That's why you need more than one lah. That's why you see it's very, very long. Okay? However, for your simple molecular, right, so your phosphorus all the way, right, you can bond that many and then it just exists as that molecule itself. There's no way to form any other bonds. So that's why they exist as one molecule, but between the two molecules, they have your ID-ID or your PD-PD interaction. Okay, can you understand? That's why it's not. So that's why when you see covalent compounds, right, you need to split covalent, large covalent and simple covalent. Okay?
Just a side question. I remember when you draw the two covalent together, there's something like induced covalent particle.
That is for your ionic. Okay, so in this case, right, if you realize that, okay, so we look at ionic compounds, right? Okay, so ionic compounds is the plus. Okay, so let's say this is the plus lah. Okay, then you have a minus charge. Okay, if this has a very, very high charge density, right? So if your Q over R is very, very big, okay, it may cause this. You see, it may cause the polarizing of your minus. So by right, for ideal covalent, okay, ideal covalent means that it's supposed to be like this. So ideal covalent, ideal ionic. Okay, so it's just two separate and then it's just interlinked. Okay, because there's no overlap. Okay, it's just I give you electrons, then we bond together, full stop. Okay. However, if there's a very high charge density, right, this means that it's very, very positive. So the electrons will want to go towards the cation. That's why you see the electron cloud, you see, it's distorted. Since it's distorted, right, this will give you your overlap. So this is your slight overlap. This is called the slight overlap. Then this is where you have your partial covalent character.
So it's AL symmetry.
Yes.
Is that why it
Yes. It's due to this thing.
So it has a...
Yes, so it's ionic but it has partial covalent character. It has a greater partial covalent character, therefore it's weaker. Yes. Because take note, your covalent bonds, right, are very, very weak compared to your ionic bonds. Okay, ionic bond is by far the stronger. It should be the stronger one lah. Okay, because your giant right here you see is a lot stronger. Because for this is trying to say that it's overlap, so your electrostatic force of attraction, right, is weaker. Because this is supposed to only have your it is supposed to have your ionic. Because why? Your ionic, right, will span many, many ions. Okay, so it's not just here, it's many, many ions by right. Okay, but because of this overlap, right, your negative charge, right, is less likely to bond with another positive charge. So your electrostatic forces of attraction, right, is weaker. That's why this one is weaker due to your partial covalent character. Okay, can? There is something similar, okay, but it's the opposite for your covalent compounds. Okay, and that's your PD-PD. So why is it PD-PD? It's because there is a change in there's a difference in electronegativity. Okay, so let's say we look at CCl. Okay, so we look at the electron cloud of CCl, right? By right, okay, for covalent compounds, right? So let's say instead of CCl, we look at CC first. Okay, so carbon. Okay, by right, the electron cloud should look something like this. Okay, so it's just evenly distributed. Okay, however, for certain covalent bonds, right, like your CCl, okay, it is polar. Okay, so instead of it looking like a circle like this, right, it looks something like this. So in this case, it will be bigger here, smaller here, bigger here. Because why? This is more electronegative, this is more electropositive. Okay, so there's an induced, this is your dipole here. Because of this, right, there is partial ionic character. Because why? When you're bonding with another CCl, right, okay, this is your positive, this is your negative. So that is your it's a bit of your electrostatic forces of attraction here. Okay, because your partial negative is attracting your partial positive. So it's our PD-PD. So this actually is simple covalence, so it's your ID-ID with a bit of ionic character. This is your PD-PD. That's why there's both ways lah. You can explain it. Okay? Usually most of the time we don't explain PD-PD with this lah. We don't say that it's ID-ID with partial ionic character. No, we just say PD-PD. Okay? But for ionic compounds, right, yes, we need to take note that if there's a slight overlap, there's partial covalent character. That's why the ionic bonds are weakened.
So when do I talk about this?
When you have a high charge density.
Like when the question asks.
Usually if they ask you to explain why by right, because by right, your AlCl3 right, supposed to have a higher melting point. However, in this case it doesn't. So that's where you have to explain, oh, due to this high polarizing power, slight overlap, therefore partial covalent character. That's why it's weaker. Okay, this is to explain the exception. Okay? But when you're talking about reacting with water, right, then yes. Because when you add your magnesium oxide and your aluminium oxide into water, right, it will hydrolyze. Okay? Your hydrolyzation, right, is also due to your high charge density. Why? Because it will in this case it will polarize your H2O. Okay? So wait, I explain that one here. Okay? So now we are looking at let's say we look at Al2O. I say Al2O3. Okay? When they add to water, your aluminium and your water. Okay? So you look at what, okay, so maybe we use we use AlCl3 lah. Okay, since you're here, we use AlCl3. Okay? So we add to water, right, we'll add 6H2O. Okay, it forms your complex ion. Okay? So in this case, it will form your AlH2O 6 3 minus plus so 3Cl minus. This one can understand, right? So 3Cl minus. Okay? However, this, because your Al has a very, very high charge density, right? It will polarize the electron cloud of your H2O. Okay, because your H2O here, right? HOH, right? There should be electron density on the oxygen atom. Okay? So since your Al is here, right? It will pull it towards. Okay? Then what will happen here, in this case, what will happen is that your Al, okay, H2O6 3 plus, okay, will react with another water molecule. And what will happen here, this is what we call hydrolysis. Why? Because it reacts with water. Okay, so he will form, I write down here, okay, Al H2O 5OH 2 minus plus H3O plus. So this is due to the aluminium's high charge density. Magnesium does exactly the same thing as well, but magnesium is only slightly. It should be under chlorides and oxides, the reaction. I think it's further behind. I think it's one part where I wrote out all the reactions, and I don't know whether there's an explanation of it. Let me look at the notes here. Okay, so it should be here, right? Yeah, so here it's on 42 here lah. So you see, here they ask you to explain. So it's amphoteric as AlCl3 has a very high charge density. So so this is for Al2O3 lah. So the idea here is high charge density. Should be chloride here. Okay, I think I never read the explanation here, but you can take note. Because in this case, right, this is the reaction with water. Because they tend not to, okay, I would say that they won't really test why they hydrolyze in water. They just have to write the reaction. Yeah. Yeah, so you need to know lah. So in this case, you see there's two ways to memorize that. Whether you memorize the two separate ones or you memorize the one all together is perfectly fine. Whichever one you find is easier. Because the pH is the same anyways, doesn't matter. For aluminium, you can do this, but for magnesium, no choice, you have to memorize both separately. I think it's page 43. Yeah. So take note lah, these are all the things. So why it undergoes hydrolysis, right, is due to the high charge density lah. Okay? Magnesium does exactly the same thing as well, but it's less likely because it has a lower charge density compared to your aluminium. Okay? So take note. That's why they undergo hydrolysis. So this is basically explaining your for your elements itself. Okay, then next we move on to the chlorides. Okay, Can? Okay. So now look at the graph of a melting point of period 3 chlorides. Okay, period 3 chlorides here, same thing, we will split into 3. So we will split part 1, okay, then we will explain part 2 by itself, and then we will explain part 3. Okay, so usually like that lah. Okay, so most of the time when you are going across the period, right, you explain in separate parts. Why? Because it goes from metallic to your sort of metallic, sort of non-metallic. Okay, so that is the middle region, and then you have your non-metallic. Okay, so that's why we always split it into 3 separate sections whenever we are explaining for the period lah. Okay, for group no need, because the group, right, the trend always goes down correctly one. Okay, so in this case for our NaCl and our MgCl2, okay, so this is due to ionic bond, so it's ionic. Okay, so this is your strong electrostatic forces of attraction, okay, between your cation and anion. Okay, then the idea here is that why is Mg greater, right? Sorry, why is Mg smaller? Wait, so the idea here is that your Mg2 plus higher charge density, so higher Q over R, so there is greater partial covalent character. Compared to, okay, in this I'm comparing back to NaCl, okay, because by right AlCl3 has the greater one. Okay, so this is comparing between these two only. Okay, because I need to give the overall and then I need to explain the drop. Okay, because they ask you to explain the trend. Okay, so you need to give a reason as to why it decreased. Okay.
So the partial covalent character is for both MgCl2 and AlCl3.
Yes, but for MgCl2 is smaller lah. It's a lesser extent.
Also for the oxides, MgO.
Yes, same. Okay, so in this case, the explanation is really roughly the same one. Okay, because honestly, it's the same compound lah. It's just what happens to your the anion. That's it. Okay. So in this case for AlCl3, okay, so in this case we will say that yes, ionic. Okay, so same thing we say your strong electrostatic lah. Strong electrostatic forces of attraction. Okay, so same thing within your cations and your anions. Okay, I write C plus and A minus. Okay, so in this case, however, Al3 plus, okay, highest charge density. So your highest Q over R. So you see there is a greatest covalent character. Okay, so this is the greatest covalent character, right? Therefore, so your ionic bonds are weakened even further. Okay.
For part 1,
Mm-hmm.
you also talk about the Q over R.
For which one? For the first part here, right? I talk about Q over Ry because of the metallic bond strength. So this is a bit different. Your polarizing power magnetic bond strength, right, is exactly the same, but they explain two different things. Because in this case, right, for bond strength, right, it's only your metal cations and the C of D localized electrons. So there's no anions inside. So that's why this one, right, represents your bond strength. Okay. However, when you have a negative anion, right, instead of it being your bond strength, right, it becomes your polarizing power. Because why? It won't drag the electrons away. Because by right, you may need to remember that Q over R ratio, right, it means that how strong it is to attract the electron. Okay, so for metallic itself only, right, is to attract your C of D localized electrons to itself. Okay, so it's the bond strength because of the electrostatic forces in between. No, that's just at the front. In this case, they never really specify because I put it under physical chem. Under chem bonding lah. Yes, you can see the metallic strength increase. Why? Because there's a greater number of electrons greater number of electrons than CO2 electrons electron. Yes, it works. Or you can talk about your metallic bond strength. Both of them are fine. Okay, but if you don't want to confuse yourself, then yeah lah, don't use your Q over R as metallic bond strength lah. It's perfectly fine. There's always more than one way to explain things in chemistry. It's just whichever one you can memorize. Because by right, in this case, majority of them are exactly the same. Okay? There is a lot lah. Okay? So, greatest covalent character therefore is the weakest lah. Okay? Then last but not least, you need to explain for SiCl4 as well as PCl5. Okay? So for this is your simple molecular or simple covalent lah. Okay, so simple covalent is ID. Okay? So the idea here, your MR of your PCl5 is greater than that of your SiCl4. Okay, why? Because you have one extra chlorine lah, and your phosphorus is bigger than your silicon. Okay, so due to this, same thing, you will explain the step by step lah. So you say that, oh, MR bigger, electron cloud bigger, therefore ID stronger lah, that's it. Okay, in this case, I will skip the writing on the E cloud lah, I'll just write ID lah. Okay, so ID of PCl5 greater than your SiCl4. Therefore, your melting point is as such, so it's an increase. Can? So usually your simple covalent is easy to memorize. It's just your ionic one, because there's a lot of exceptions.
So whenever they have like a slight increase or decrease, you have to
Yes. Because in this case, they ask you to explain the trend, okay? So the key thing here is they ask me to explain the trend. So you need to specify, which is a bit difficult lah, okay? Because it is a lot to write. Okay, for 3 marks, it is quite a bit to write lah. Okay, but that is the sadness of, yeah, can go ahead.